Okay. Hello, everyone. Welcome to the third session of Horizon Summer School 2025 Introduction to Quantum Communication. Today, we are taking a step into one of the most fascinating frontiers of modern physics and technology. We'll be talking about uh, something about quantum communication. So, we'll build up from the basics and gradually see how quantum mechanics reshapes the very way we think about information and security. So today we'll be talking about the following topics. We'll talk about encryptions and security, and how classical and quantum are different, and what makes quantum such a hype topic in the recent past. We'll go over a few basics of quantum communication, a few quantum protocols, and some recent developments that are going on around the world. And taking you through this journey will be myself, Lekashri, along with Ajaya, Nikshay, Balendu, Arudra, and Tanu. So, by the end of this session, you'll see how the weirdness of quantum physics becomes a powerful tool for the future of secure communication. So, let's dive in and start off the session. So, Ajaya will be uh, beginning the session.
Hello, guys. I am Ajaya, and what I will be doing is introducing us to the basics of encryption, and we'll mostly go through the basics and the classic side of encryption, and I'll be setting the tone up for the rest of the session, helping you get that before we dive directly into quantum computers and all of that. Okay, uh, so let's start. First of all, from the very basics, what is encryption? See, the whole point of encryption is to send a message from you, the sender, to a specific person, the receiver, knowing that nobody in the middle has intercepted it. No, being like you're sure that nobody else has intercepted it, and the message has reached only the desired receiver. So let's, for example, let's say you want to send, text hello to someone. You don't want anyone else to know what you send. So what happens, like, if you just send hello over your channel, like if you send the hello text as it is, and if somebody intercepts it, like if somebody gets in the between of your channel, they'll just see hello. Okay, he sent hello hello. Okay, he meant this. So we don't want that to happen. So what we do is we apply changes, steps, algorithms to the text, so that we know what the text was, and then the receiver will know what the text was, and to somebody else it will be gibberish, random letters. So, what's encryption? Encryption is the process of transforming plain text, which is our common language, readable information, into ciphertext. Ciphertext is in the image, as you can see, this random string of letters that will, and what you will be using to make this transformation is called a key. So key you can think of as a set of steps or algorithm that you can do to your text to make it into a random shuffled text known as ciphertext. So if somebody intercepted, let's say, this message instead of hello, they could not guess what the text was, like SNIFGN. Can you guess what the message was? Unless you know what has been done, you cannot know what the ciphertext means. A basic example will be, what if the key was to shift every letter by two, like if it was A, it becomes C becomes E. So it sort of becomes a bit jumbled. I mean, it's not that secure, because like somebody, if they put effort, they can make out that you're shifted letter. But you get the point, right? You do something to the plain text to convert into ciphertext, and then you relay that ciphertext over the channel. So that is the whole. This is what basically encryption means. Okay, so why encryption matters? You guys can guess. Encryption, it protects sensitive data. Like, you guys don't want, we don't want like military conversations, government conversations getting out in the public, or someone else knowing it. So that sensitive data, encryption protects. It makes sure only those people who should know information will know that information. The second is defense against threats. Now, threats in this modern digital era are like, there are a lot number of threats, like hackers, cyber thieves, identity thieves, the cyber criminals, and all of those. You don't want them getting your personal info, and that's what encryption protects. The next is ensuring privacy and confidentiality. You only this goes hand in hand with protecting sensitive data. You ensure that your conversation is private and it is confidential with the receiver. And lastly, it builds trust and authenticity. Like, coming to think of it, why do we use WhatsApp? No, and not some just other like good app, any better app. Like even tomorrow, if a better app comes along with features, but it's not encrypted, it does not say that, hey, we're encrypted, nobody will be using it, because these platforms like WhatsApp, Telegram, they have built that trust and authenticity due to their encryption protocols. Like we know it is secure because of those protocols, and we use those apps because of that. So that's what encryption gives you in this day. It gives you defense and trust. So step further, what will be the types of encryption? So broadly, there are two types of encryption. The first will be symmetric encryption. Now, if you will remember for the first slide, I told we use something called as key, right? A key is a set of steps or algorithms you apply to the original text, right? So this division comes basically mostly based on the key. So in symmetric encryption, as the name suggests, you encrypt and decrypt using the same key. And the other example, as you can guess, is asymmetric encryption. And in that, you use different encryption, you use different keys to both encrypt and decrypt. Like in the example I gave, shifting every letter by two, like A becomes C and C becomes E. What do you think is the type of encryption? It is symmetric encryption because what did you do to convert into ciphertext? You shifted every letter by two. And to convert it back into normal text, you again shift the letter by two, but forward and backward. But the step remains the same. Shift every letter by two. That is the key. And you do it for encryption and decryption. So that's asymmetric encryption. And as you can think, in asymmetric encryption, you do something to encrypt it and you do something else to decrypt it. We'll go through them in detail. So first of all, let's go through symmetric key encryption. So as you can see in this image, we have an original text. We apply a symmetric key and we convert into ciphertext. So as in shift every letter by 2, 5, 7, etc., etc. You know, so that is a symmetric key. And when the ciphertext reaches the receiver, what he will do is he'll take the key and he'll see like, oh, every letter is shifted by two. So what I must do is shift every letter by two backwards. So he will do the same thing but backwards, right? So in a way, he has done the same thing, shift every letter by two. So did you understand? Like you use the same key twice, both to encrypt it and decrypt it. So this is symmetric encryption. So a popular example of symmetric encryption is AES. AES stands for Advanced Encryption Standard. This is like WhatsApp uses a bunch of encryption methods, like mixture of many methods, and one of those is AES. AES 256 is the name of the encryption method used in WhatsApp also. And even historical methods like Caesar cipher. Now, Caesar cipher is the example I gave, shifting every letter by some digit like 2, 3, 5. That is known as Caesar cipher. So all of these are example of symmetric encryption. So, can you guys think of what a problem in this type of encryption can be? Like, I need to go ahead and like think. If you were a hacker who want to, tap into a conversation that is using this encryption, what will you focus on? Like, what is the weak point in this conversation? Uh, the thing I want you guys to focus on is the symmetric key. You know, when you use a symmetric key to encrypt it, and you send the ciphertext to the receiver, even the receiver should have the symmetric key, right? Without that, they can't decrypt. So you need a way of sending the symmetric key also securely. So if this key is compromised, the whole conversation fails. Like if somebody else has a symmetric key, even they can read the conversation. So you need to guarantee that this key stays between you and the receiver. So that is one, you can say, drawback of this encryption, that the key needs to be very secure and you cannot risk this key in other hands. So I think that's one drawback, but this is faster than asymmetric. We'll go to asymmetric encryption. So asymmetric encryption, what is it? As I said, there are two keys. Now you are not using a single key for both encryption and decryption. What you're doing instead is you have two keys: public key, which, as the name suggests, can be public. You can, you know, in symmetric encryption, you cannot tell your key, but in this, you can tell your public key out, and then there's a private key which you must keep to yourself. And basically, how this goes is this public key and private key are somehow related. Let's say by a mathematical problem, you can, in theory, derive them both. So what you do is, you broadcast to the world that, hey, if you want to send me a message, secure message, please use my public key. Now, what is a key? A set of steps to convert plain text into ciphertext. So you say, please use this public key to convert your text, your message, into jumbled words, so that I can use my private key, and only me, who has the private key, can convert that ciphertext back into its original message. So in a way, you have made this conversation secure, and this has an advantage over the symmetric encryption, because one, you don't have that much risk of, the key getting leaked and all of that. And the second is, in asymmetric, if you guys think, for one conversation I need a symmetric key. If I want to talk to someone else, I need another key. And if I want to talk to 10 people, I need 10 keys, right? So every person, like every conversation, needs a key. And when you have a large enough network, the key, generating them, distributing them, it becomes very tough. So in symmetric encryption, you need one key for every conversation, but here you need a set of public key and private key per user, right? So if you give a public key and private key to one user, then they're set, they can carry out their conversations with other people, and it will be secure. Because public key, so again, public key is what they use to encrypt, and private key is used for decryption. Now, public key and private key are kind of related. Like, you can derive, in theory, derive public key from private key, but that is very difficult, as we'll see further. Okay, wait, let us, can you think of any drawback to this type of encryption? Uh, I think one of the ways this encryption can be compromised is if the public key you're using is wrong. Like, when you use a public key, if someone gets in the middle and, presents a person to you, and you trust them with their public key, then the man in the middle will get to know your conversation, right? Like, they will read your message, then relay it to the receiver, and then they'll take the receiver's message and then they'll relay it to you. Like, you, there is no way that you can figure out that there's a man in the middle. And these types of methods is called man in the middle attack. So this type of encryption is kind of vulnerable to that attack. So you need to be taking public keys from a trusted source and not from here and there, so that you know you're talking to that person itself. Uh, and that's it for asymmetric encryption. Next, we'll see where do we use encryption and all of this in our real world. First is web browsing HTTPS. You guys must have heard of HTTPS, right? So what it stands for is HTTPS Hypertext Transfer Protocol, and S stands for secure. It is secure because it uses these encryption methods, and every time you log into a website, establish a connection with the server, you give your details, you fill in a form, you take contact someone through a website, every bit of information is encrypted to the server, so that nobody else can come in between and steal your details before it reaches the server. And the next is messaging apps, as I told, the Signal, WhatsApp, Telegram, and all of those text messages we use because we know they are encrypted. They are safe. They use, if not one or a multiple of encryption methods to make sure it's like very secure. Next is online banking. Online banking, when your transactions, you say to the bank server, like UPI and all of that, you see the bank server, hey, this is my password, this is my account number, this is the amount I need to pay this person. So you don't want that information to be compromised. So online banking like relies heavily on encryption. And then the next use case of uh, encryption is cloud storage. Cloud storage, as in, yeah, Google Drive, and all of those. When you Dropbox your files into the cloud, every bit of your files and all of that is encrypted, and it's secure to the server and to the cloud. Then next is using VPNs. Now, what do VPNs do? They hide your IP address, right? So to hide your IP address, they first need to encrypt it, so that the website you're trying to connect to does not see your original IP address. So VPNs actually rely on their basic foundation relies on encryption. If there's no encryption, there are no VPNs. So these are the real world uses. Now, what makes encryption secure? Now, if you will remember, in asymmetric encryption, I told if you have the private key, in theory, you can get the private key. So why do we not see that happening? Why do we, if I give a public key and I give you a task to find out its private key, what makes it hard? What makes encryption secure is complex mathematical problems. These encryption methods, they assume that you cannot solve that problem. Like the problem between the private public key and the private key, there's a mathematical problem. Like that, if you solve it, you will get the private key. But these just assume, and they are right, that you cannot solve these problems. These problems are like way more hard. And if you give these to a classic computer, this will take, I don't know, thousands of years. And if you give it to a supercomputer, it will take like hundreds of years of computation just to solve one problem, just to go from one public key to private key. These mathematical problems, like large primary factorization, ecliptic logarithm problems, and all of those are like very tough, very computationally intensive, that it will take a lot of time to solve it. The time is actually more than a human lifetime. So that's what makes it secure. So why do we trust this encryption? Because we know that there is no, computer right now that can crack that problem. So if they can't crack the problem, they cannot crack the encryption which is based on that problem. So we know it is secure. The second method is secure key management. Now, in symmetric key, I told the symmetric keys need to be very, very, safe. You cannot risk it being endangered. So what most of the protocols, encryption protocols do is they use asymmetric encryption to send the key. Do you understand? Like, get this? They first use asymmetric encryption to send the keys, not the whole message. And when the key reaches them both through an asymmetric channel, then the original text, the actual text, is transferred through a symmetric channel. This is known as hybrid encryption. So they very securely handle your key. Like, they use hybrid encryption. They You may ask, like, if asymmetric is so secure, why not just transfer everything, like whole text in asymmetric only? The problem is, because I told it uses public key and private key, those are a bit comparatively slow, like, and more computationally intensive. Like, a computer will take more time to run asymmetric encryption than for a symmetric encryption. So what we do is we just share the key, and when we know the key has been securely shared, we'll just go ahead and talk through symmetric channel, because there are no other flaws in the symmetric channel except that the key is a bit sensitive. So if you handle the key effectively, you can make sure that these stuff are very secure. So these are the both ways uh, how we know encryption is secure: complex mathematical problems and secure key management. Now, we have seen about encryption. Let's go for an example. AES. Just does anyone remember AES? We skimmed through it in symmetric encryption, right? So AES is a type of symmetric encryption. It was developed by NIST. NIST is actually a government-funded department of the US. They first developed this AES, and since its creation in 2001, it has undergone many changes. And the present day AES is like very secure. Like, it will take even a supercomputer hundreds of years, like 500 years, to break this AES algorithm. So it's very secure. So we'll just broadly go through how it works. Okay. So we have plain text, plain text of 128 bits. So what it does is it takes your information, breaks it down into blocks of 128 bits, and for each of those block, it applies whatever follows. So what follows is, it has one key, right? Because it's symmetric, it has one key. So there's an step called key expansion. So one key is expanded into k0, k1, k2, and k, so on until kn. And for plain text, at one, so remember what a key is. A key is a set of steps, right? So you apply that key at the plain text, like shift. As I said, like, is something, this is far more complex. The example I'm giving is like way too simple, but you get the point. You do something to the plain text to make it a bit jumbled. So yeah, round one happened, it became a bit jumbled. Then round two, round three, round four. At every round, it becomes more jumbled and jumbled and jumbled. And what happens in every round is, mix of substitution, permutation, mixing, and all of that. No, you do all of this at every round, so that at the end of this, all of these rounds, actually round n matlab, like, the number of rounds depends on this size, like 128 bits. So there is AES 128, AES 256, and all of that sorts. So if there are more bits, then naturally there are more rounds. So at the end, what you get as cipher text is like very, very jumbled. And even the length, like, if this had a length of, like, 5 characters, then ciphertext will have like 10, 15, so that you can't even guess what the word was. Like, and changing one letter in the plain text will change the whole ciphertext, like, completely and differently every time. This is known as avalanche effect. Okay. So you cannot, even if you have a bunch of ciphertext, you cannot possibly predict, like, as in, if I in the example I gave, shifting every letter by 2, if I give a set of, like, 10, 20 ciphertext, you can probably with some effort make out key, okay, this letter appears very much, this is the same length as hello, this can be hello, and all of that sort. You can do that type of analysis, but that fails in AES because first of all the length is different, and second, like, it is way different for every letter changed. If you, I'm saying, if you change in only one letter, the ciphertext changes completely. So this is a very secure algorithm right now, which is used in WhatsApp also, as I said. So where it works, HTTPS. HTTPS uses AES, messaging apps like Signal and WhatsApp. WhatsApp actually uses a bunch of other methods also. Like there's a method called as curve, then there's AES, and then there's other also, which is like collectively known as Signal protocol, and they use this to encrypt all of your messages. So, and the next, disk encryption, file archives, VPNs, and secure email. All of these are heavily dependent on AES. So, yeah, these, you can see how much important AES is right now in this, especially in this digital world, in the coming, AI world also. These encryption methods will, play a huge role, and for the foreseeable future, these algorithms are secure. Okay, so next, this AES was a symmetric example. Next, we'll go to a popular example, which you might know, which you might have heard of, is RSA. RSA is an asymmetric type of encryption, meaning it has a public key and a private key. Now, as I told, a public key and private key are related by a, example, a mathematical problem. In this case, it's large prime number factorization. So if you guys can, like, see in the image on the right hand side, or on the sixth and seventh point, there's a public key, which is a function of E and N, and private key is a function of D and N. Now, what is N? Like, which is common. N is a product of two large prime numbers, P and Q. So N is equal to P into Q. So in theory, if you had a public key, and like N, you can actually derive the private key. But what makes it difficult is, in the step of deriving the private key, you will have to factorize n into p and q. And the fact is, to factorize n into p and q is apparently a very hard problem for classical computers, especially if p and q are like very large, like, like 6, 7, 8 digit numbers, 8 digit prime numbers. Those are, like, it's very difficult for the computers to factorize this, and it will actually take a lot of time. So how RSA works? First is key generation. On the left hand side, we see first step is key generation. Two large prime numbers are chosen, and from them a public key and a private key are mathematically derived. So they are related. And then encryption process, like, you keep the private key and you tell to the whole world, see, hey, this is my public key, if you want to send my message, please use this key. So someone uses your public key, they send you a message, and you, using your private key, decrypt that message. So in this process, how do you know you are secure? That's because, nobody can factor large prime numbers, the p and q, from the n itself. And actually doing this will take you, like, as I said, 500 years for a classic, for a supercomputer, and for a classic computer it will take like thousands of years, right? So what's the problem here? No, what's the problem for hackers? Somebody who wants, to listen to your convo. What is the core security feature of these, RSA and all of these encryption methods? As I told, it is the assumption and actually fact that mathematical problems are hard, like really hard to solve, and they aren't really impossible. As I told, you can derive, but they're just computationally very intensive, very intensive. That RSA relies on factoring large prime numbers, and ECC ECC is another type of encryption method. It depends on discrete logarithm problems. Even those are similar to this factorization problem. This will take hundreds of years, to actually solve it. So what you can ask is, okay, boss, right now my computer cannot solve this. Okay, my computer cannot factor large prime numbers, but computers are getting, what do you say, smarter, faster, like every year. If you compare like 10 years before and the computers now, we are a lot ahead, right? So the question the question is, what if a more powerful computer comes along? You told we need 500 years of computation to solve this. What if somebody builds a computer tomorrow that can do it in 5 days or like 5 hours? What happens then? You might This is a natural question, right? And this is a good question. Like, if that computer comes along and a common person can get their hands, it is that commercially viable, that sort of powerful computer. As you can see, this RSA lock, which was locked before, you can basically unlock it using that computer. Now, what will happen if this powerful computer comes along? Do we have one? And all of these questions will be answered by my friend Balendu. Balendu, please take over.
Yeah, thank you. So, hello everyone. My name is Balindu, and I'll be answering this question and be talking about some more things. So, the straightforward answer to that question is yes, we do have such computers, but they are not big enough and powerful enough yet to do something meaningful or to break RSA or to break any encryption of any sort. So obviously you might have heard of these computers, and they are called quantum computers. And yes, the computer that you see on your screen right now is an actual quantum computer, and yes, they look exactly like that. They look very cool. uh, and so in the next 15 to 25 minutes, we'll go over some things about quantum computing and why is it so powerful and what makes it powerful. So we'll talk about qubits, we'll talk about measurement part, we'll talk about cryptography, and then we'll finally get to why all of this is relevant to our session and why is it relevant for communications, right? Okay, so we'll start off by something very basic, which is classical versus quantum, right? So we are talking about how quantum computers are much better than classical computers. So let's just get at that, right? Why is it that, and is it actually true? So classical computers, they everyone knows this, they use bits as their. So okay, so before talking about that, we'll set a premise, right? So the premise is that any computing system, right, whenever you want to perform a computation, it's basically that you have some data, right, and you have some set of operations that you perform in a sequential manner in order to get something out of that data, something useful, right? So say I have two numbers, I want to add them, right? So I'll get something useful out of doing that, and that is basically a computation, right? So classical computers, the ones you are using to watch this session, the one I am using to do this session, use bits as their sources of information, right? Now we know that these bits can either be 1 and 0, analogous to high and low, and this limits the amount of information that you can encode inside a bit, right? So say 2 bits can only encode 4 states, 3 bits can only encode 8 states, a single bit can only encode 2 states, which is 1 or 0, right? So on the right hand side of your screen you see a sphere, right? And uh, that sphere is called a Bloch sphere, right? So what quantum computers use and what gives quantum computing its power is these qubits, right? So I'll tell why that sphere is there, but we'll go and understand more about these qubits with the analogy. So basically, a qubit can be any single point on that sphere. Yes, the qubit can be anything on that sphere. So basically it has infinite amount of states. We'll understand this slowly how it works. We'll go over this using an analogy of a coin, right? Uh, so let's get started. So now imagine a coin, right? And also these qubits act really funny. We'll understand it. So imagine a coin, right? Imagine you throw a coin. You are flipping the coin, and I want you to imagine the coin while it is in the air, right? So and say the coin is spinning really fast, not like in the gif shown here, but say it's spinning really fast so that you can't see what exactly is the head you're looking at, right? So while it's in the air and it's spinning really fast, you can't tell what is the head which is facing up, say, which is facing right or whatever, right? You can't say it deterministically. But what you can do is say that the coin is in a state where the face which is pointing up is a probability, right? Is a probability where it can be either heads or tails with the probability of 50%, right? So you can say that, you can theoretically say here that the coin here is in a probabilistic state where the probability of it being heads and tails is 50-50% in an ideal coin, obviously, right? So now say that you have a coin in which you can control the probability of it being heads and tails, right? So now we have said that this coin, right? So let's try to put the concept in a line. So what that would be, that while this coin is in the air, and since we cannot tell exactly what the head is at that moment, we will say that the state of the coin is in a probability of either states that it can land to, right? So it will be something in between, right? It will be something in between, right? Now let's extend that to two coins, right? Now say you are flipping two coins and both of the coins are in the air at the same time, both of them again spinning really fast. And let's try to write this state down in a mathematical expression, right? Now again, both of these coins, we can control the state, we can control the probability of them being heads, both of them, right? We can control them independently of each other, and hence you can write that while the coin is in the air and it's spinning, the state of the coin at any point of time is something like a into hh plus b into ht, c into th plus d into tt, where hh, ht, th, and tt tell what the phase might be, right? And these abcds are some quantities, some coefficients that you add to represent the probability of that thing happening, right? The probability of that thing being at that moment of time. So a very obvious thing that you can observe is that the sum of the probabilities has to be 1, right? So say here we write that mod a square is the probability of this system being in a state of hh. Then obviously you can write a square plus b square plus c square, like mod a square plus mod b square plus mod c square plus mod d square must be equal to 1, right? The system will be in some state, right? Now, let's get to why this is interesting and why this analogy is correct. So so in the system, we have defined the state in a way that it is probabilistic, right? It is not in any of these states exactly. So it's not exactly into HH, but it is in HH to some extent with some probability. It's also in HT with some probability. It's into TH also with some probability. It's also in TT with some probability, right? So now we are also saying that we control these values of A, B, C, and D, right? We control these probabilities. So what we have done with this system is that it is in a superposition, right? Now if you like to this huge word that is goes around with quantum, it's in a superposition of all these states. So what that basically means, that it is simultaneously in all of these states with some probability, right? This is really important to understand, right? So these coins, right, now we are saying that it's a probabilistic state, right? We got to the point that this state is a probability. So a probability is a thing that you can't quantify, right? So I can also say that this state of these two coins represents infinite number of states, right? Each of them having their, like, so there's a probability, right? So corresponding to each of the probabilities there will be some state, right? So in a sense that it can codify. So now we'll get back to the premise of bits, right? Bits were only able to codify two states, but now we're saying that we have an infinite number of states, right? It can be HH, it can be HT, it can be TH, it can be TT, or it can be all of them at the same time with some different probabilities that we control, right? So in this system that we have just defined, we are saying that we have an infinite number of states, right? We have, so now what if you are able to codify some information, right? So bit is 0 and 1, right? So now let's say you're able to codify some information related to the states of this system, of said system. So now since we have infinite number of states, we can theoretically, right, theoretically codify an infinite number of information inside the state. So that's a lot to take in. I'll say it again. Since this state is in a probabilistic nature, we can theoretically, if we are able to codify some information into these states, we can theoretically codify an infinite number of information inside the state, right? Inside just a system where you have two such coins. Now obviously it does, such a system like with coins doesn't physically exist, right? You can't have a coin which is spinning too fast. There's a limit. You'll have a faster camera, you can look at it. And so, but there's an analogy. Now I'll tell you that these kind of states and systems actually exist. And again, these systems and states are qubits, right? So these qubits, how we actually use them in the real world are maybe electrons. Like electrons, uh, you can do it with the spin of electrons. It can be either half, it can be either minus half, or anything in between in a quantum state, in a qubit. And you can use it as a qubit. You can use photons, the polarization of photons, right? You can also use atoms, like physical atoms, and many other things to actually model such systems. So again, we have found a way of encoding infinite number of information. We are hearing it completely right. Infinite number of information inside a state. Okay, so we set the premise of computing where you have some information and you apply some computing to it. Now we are saying that you have a way to portray infinite number of information into some state. So now can you actually compute on it to get some work done, to do something useful? So that's where quantum computers come in, right? Quantum gates and all, what you have heard. So before that, we'll get to another concept in quantum computing, which is quantum entanglement, right? So now we said that the probability of something happening has to be 1, right? So the sum, as you can see on the screen, the summation of uh, ABCD mod squared has to be 1. Now say I put these two coins in across a galaxy, across a whole galaxy, right? And I am somehow able to change the value of B, right? Mod B squared. Now if reality exists, right, if it is true that the sum that the coins have to be in some state, which is absolutely true, the values of AC and D have to change accordingly, right? So this is something known as quantum entanglement, where if you change something in one qubit, there has to be a similar change in another qubit in order to assume reality, right? So that something exists, right? Okay, so we'll move on now. So we have the concept, right? So again, the same thing. Since the state itself is a probabilistic, there are infinite number of states, right? And quantum entanglement, right? Now let's get to the catch. Like I'm saying that you have infinite number of uh, states, and you can do infinite number of you can store infinite information in just a qubit. Let's get to the part where I say that, okay, so there's a catch. So the catch is quantum measurement, right? So these qubits are actually very fragile units, right? So the thing is that these they physically exist in a superposition, as we said, but as soon as you measure them, they fall into one of these states, right? So with the probabilistic nature, right, so it will happen with the probability that you have defined earlier, but they will fall as soon as you measure. So the thing is, these qubits behave in the way I have outlined when we are not looking, but when we start looking, they behave like normal bits. They're either 0 or they are 1. So now one might say that how are you ever going to do something, do something useful with such a thing, right? So you, when you're not looking, they seem like gods, like they can do anything you want, but then as soon as you start looking, they become normal humans, they become 0 and 1, right? But this is where some of the algorithms in quantum computing come. So we'll talk about some of these algorithms, and we'll talk about how we can't really talk about how they work fully, because they that is beyond this session, but we'll talk about what are the implications of such algorithms and how it affects encryption, right, which is our main goal. So how you do a usable computation is that, say this image, right, the computers per se in between is the quantum computer. You put, so the thing you're putting in is supposed to display the infinite number of states. You put it inside a quantum computer, you do a computation which is important to you, and then you get a result, right? Now this result is obviously not readable to you per se, right? If you read it, it will fall into some one of the states. You will put this back into a quantum computer, do some further computations, and try to, estimate some of the outcomes that you can get. Now you can't, until now what we have been able to do, you can't really get to know all of the computations that you performed, but you can get some ideas, right? So you can get some useful results. We'll explore how good these results are, right? So we'll talk about one such algorithm which is really famous. It is known as the Shor's algorithm. It was found by MIT professor Peter Shor in 1994, and it solves a very particular math problem, right? So it allows you to factor large numbers into two prime factors. If you have been hearing the session properly, you would know that such a problem is used in encryption, right? This is basically the premise of RSA encryption, and basically the premise that in some ways used by WhatsApp, is used by every other thing that you are using, right? So again, you say that, okay, so I'll put up a number as well. So the classic RSA that everyone uses in the world right now is it's 2048 bits long, right? So the prime number you're trying to the number you're trying to factor is 2048 bits long. And for a classical computer, right, the best computer you have, the largest supercomputer in Japan, will take about 13.7 trillion years to do that. So that is so that's basically 13.7 billion years, sorry 13.7 billion years. So that's basically older, that's not even the age of the universe. The universe is less old than that, so basically it's not possible on classical computers. But a quantum computer, on the other hand, the key thing being, if you have a large enough one, we'll get to why they are not large enough and what are the challenges. But if you have a quantum computer which is able to perform this algorithm, then you can do it in 8 hours. You can do this, you can break RSA in 8 hours, right? So that's a really scary thing to say and to hear, and to really understand that it's really scary, right? So we'll talk about another quantum algorithm. So uh, another thing that is really hard for classical computers to do is unstructured search, right? We'll understand what this term means, unstructured search, through an analogy, right? So you, on your screen, you see a kind of room with lockers. So I want you to imagine that this room of lockers is very, very large, something you've never seen. Like, say it has 10 to the power of 9 lockers, right? A very absurdly large number, right? And now one of these lockers is yours, right? And you have your key, right? You have the key, okay? uh, but you don't know what locker it is, right? You don't know what locker it is, right? Now you want to go and find your own locker to get something you have, and say it takes you 5 seconds to go to the locker and check uh, if it's correct, right? If it's yours. So in the best case scenario, which is if it's whose probability is 10 to the power 9 minus 9, is that you find it in your first go. And the worst case scenario is that you find it at the very end locker, you check. But we'll take the average case. On average, it will take you 10 to the power 9 divided by 2 steps to operations. So like, you will have to go and check 10 to the power 9 divided by 2 times to find your own locker, right? So this time frame that we're talking about would be 10 to the power 9 divided by 2 into 5, right? 5 seconds being the time it takes for you to go to each locker and check. So that number turns out to be about 80 years, right? It turns out to be about 80 years. So it will take your whole lifetime to go through and find your locker on average. That is on average. It could be much worse. It could be a maximum 160 years, right? For a similar problem, if you're able to codify these lockers and your key inside a quantum computer, and you have to go, and the quantum computer tells you which locker to check, right? Then it will take then and if you multiply that by the time you're taking, it will take you about 1.83 days, right? So that is the speed up we're talking about here as well. From 80 years we go to 1.83 days, right? Because the Grover's algorithm, this algorithm that we're talking about, it's the search algorithm for unstructured search. It takes about n to the power of half operations to find the correct key. So basically what I'm trying to explain to you guys is that these computers are really, really good at certain things. Yes, these things, but where they're good, they're really good. They can do much better than classical computers, right? uh, there are many other applications for these quantum computers, and since these quantum computers are using the very basic things in nature, right? They're using photons, they're using uh, electrons, and they're using quantum mechanics as their basic model, to perform computations. They are very good at modeling the natural things, right? The surrounding nature. For example, they can be used, and this has been proven that they can be used in drug discovery, improving solar panels, batteries, optimization issues, or basically anything that involves a chemical reaction can be improved upon by a quantum computer, right? And as you can see some more things, the cryptography and security is obviously what we're talking about, and they're already used to solve many optimization problems around the world, right? Now you will say that, okay, these are very good, but why don't I see the change right now, right? So that is because it's very, very, very hard to make such computers, right? So you there's another image of a quantum computer right there, and yes, they look like that, and they look like that for a reason. The reason being that the qubits, right? So we talked about how the qubits are disturbed very easily, and they fall into some state when you look at them. They need this disturbance is not only from humans, from us. It's also from thermal fluctuations, it's also from temperature, it's from everything and anything, right? It's from light, it's from anything that can come their way. It's any sort of energy. If you give them any sort of energy, they are destroyed. The qubit is destroyed. They're not anymore codifying any information. Also, a cool fact, these quantum computers are some of the coldest places in the known universe. They are kept at a temperature of around 10 millikelvin, which is something you don't observe in the whole universe that we have looked at, right? So the thing being is that they're really, really hard to make, right? The engineering challenges are humongous. But again, the thing is that the whole world is moving at a steady rate, right? You see, there Google is there, this many companies, some of which are there on the screen, some of the largest ones, which are pouring money, so much money, so much manpower, so much intelligence into solving the engineering challenges related to quantum computers, right? And the thing being that they are coming very soon. right? So there was some plan laid out by IBM Quantum Computing about 3 years ago, and they are right on track. And now they have laid another plan for the next 5 years, right? And considering the history, they have been on track and they might be on track. So after 5 years, we might have a quantum computer which can do a lot of things, right? Maybe even break encryption. And another thing that I want you to understand is that since these engineering challenges are so enormous, the community as a whole is focused on making of is focused on solving these challenges first, right? So they are not focused on doing on getting to know what you can actually do with these computers right now. The drug discovery part, the everything has been theorized. There are algorithms, but these algorithms are not good enough, right? So we don't know if in a year some algorithm comes out which is better than shor's, uh, which can be implemented on a quantum computer which we have right now, right? So the threat is imminent, right? The threat is imminent. So now, in the last 15-20 minutes, we have established that quantum computers are really powerful, right? And the fact of the matter is that we rely on solving very tough mathematical problems in order for us to stay secure, right? So that everything is encrypted, and quantum computers are a threat to that, right? So we'll get to why this is relevant to a communications session, right? So the inherent flaw in modern communication systems is that whatever the 5G system, how it works, right? So there's a tower somewhere, and that tower is throwing out waves in all directions, right? So say the tower is meant for a 1 kilometer radius. So everyone in that 1 kilometer radius can get the signals coming to my phone or my laptop, right? Which might have contained some very important message, right? And if someone were to figure out a way to decrypt this message, so the message is encrypted, right, by the ways told by Ajay, right? Then it is a huge, a huge threat to everything we see around us, the whole digital world, our money, everything. It's a threat to everything, right? uh, Also an issue is that people, what they are doing right now is something called save now decrypt later, right? So what they'll do is, they know something very important is being communicated right now, so they'll save the message, they'll save the cipher text, so as to say, somewhere right now, and then they'll wait for quantum computers to eventually come up, and then they'll decrypt it when they come up, which is again a very scary premise. That's why one needs to figure out a way to communicate at range with someone digitally, such that they know that no one else has looked at that message, right? That is not guaranteed by what encryption is today, right? But can be guaranteed through some new technologies known as quantum communication, the session today, right? So uh, a solution to that, these flaws, is quantum communication via QKD, quantum key distribution. There is an image of IIT Delhi doing it, right? IIT Delhi recently did it with DRDO, probably soon as, hopefully. So my friend Arudra will take up the QKD part and explain to you how that is better than what we are doing right now. So Arudra can take up.
Hello everyone. So this is Arudra. I'll be taking over from here. So now, as Valendu explained, you guys would have got a basic idea of how the classical encryption methods can be broken down if there exists a quantum computer, like if they are manufactured. So they are being manufactured. So this is where we get a need to go for some other type of classical encryption methods. Uh, yeah. So this is why we need a quantum communication method. So what basically quantum communication means is it is a method of transmitting secure information using the principles of quantum mechanics and the quantum entanglement concepts. Here we encode the information in the quantum states of photons, like the quantum particles. So why we use quantum cryptography in the sense, yeah, as Balenu explained throughout, the classical algorithms can be easily broken down by a quantum computer. So only a quantum method can be safe towards another quantum attack. So that is why we go for this type of communication. Now, what makes a quantum communication secure is that we use qubits mainly. Like qubits in the sense, these are not like the classical bits which are zeros and ones. These are like mainly photons which can exist simultaneously in several different states. So we use these to transmit the information. So any eavesdropping effort in between, like made by some hacker or someone, will never go unnoticed, as we use physical laws additional to the mathematics here. Like in the classical encryption methods, it is mostly the maths which is involved, right? Like the algorithm, like the mathematics, it is pure mathematics, it is very predictable. So here we use the unpredictable nature of quantum mechanics, the photons and their states. So that is why this is more secure than the normal encryption methods. And here we use certain laws, right? Like everything works depending on certain basic laws. So let's look into what those laws are. Like there are basically four main laws, and the first one is the superposition principle. The quantum particles, like the photons, can simultaneously exist in several different states at a particular instant. Like if we don't see them, they can exist in all the way possible with certain probabilities of each one. But as soon as we measure them, we can conclude that they exist in this state. So they will collapse into one of the particular states. So this is what the superposition principle states. Unless and until we measure them, they can exist simultaneously in several different states. So the real world depictions and examples are like, from the school time, we know the electron's position and velocity cannot be predicted. Like the Heisenberg's uncertainty principle states that. And the next one is the Schrodinger's cat experiment. Like unless we open the box and see what the cat is doing, like if it is alive or not, we don't know. It might be dead as well as alive simultaneously. So this is one of the best examples for the superposition principle. And the another one is a polarization in the sunglasses or camera lenses. Like for example, if you take certain amount of light and you keep a horizontal filter, so the light passing through it will have every component of light which is horizontally polarized. It doesn't have any vertically polarized. So if you keep a vertical filter, then you won't get any light passing through it. But if there is a second case, like you pass the entire bulk of light through a horizontal filter and then keep a 45-degree angle filter, that is a diagonal filter, then certain amount of light still passes through it. So what this means is that there exist intermediate states and not the completely final states in the case of photons or any quantum particles. So these all are the examples of superposition principles in daily life. And next one is the entanglement concept. Entanglement in the sense, like if you take two particles, here they are photons, and no matter how far they are separated, their states will be interlinked. So if you change the state of one photon, then the state of the other photon will automatically be altered. So like this, you can understand it, right? So if there is any attempt to break the information encoded in one particular photon, it will change the state of the other photon, so it can be noticed. And this is what is mainly being used in the E91 protocol, which will be explained shortly. And the next principle is the no cloning theorem. No cloning theorem states that it is impossible, like completely impossible, to replicate a unknown quantum state. Like for example, as I said, each photon exists in the superposition of several states. So before measuring it, we cannot predict its state and we cannot clone it. We cannot replicate it. This is what is said in the no cloning theorem, and this is what is the basis for quantum communication, that is the quantum key distribution. We cannot replicate the states of a photon unless and until we measure them, and as we measure them, it will be noticed by the privacy like factors, like it will be noticed by the security systems and etc., and the presence of the eavesdropper will be detected. And next is the measurement problem. Like what measurement problem means is, like as I said, when you measure, this introduces errors into the photons. So these errors are called as like this process of framing errors. Like the measurement causes errors, right? And these are called as the measurement problem in quantum mechanics. And that error rate is called as the quantum bit error rate. I'll explain this shortly after I explain the protocol so that it will be easy for you to understand. So for now, just keep in mind that the errors are introduced and this is called as the measurement problem. That's it. And here we use a basic convention throughout this communication channels and everything. The sender is called as the Alice and the receiver is called as the Bob, and any potential eavesdropper present in between is called as the Eve. So now let's look into the first and the most basic and easily understandable protocol, the BB84 protocol, which was developed by Charles Bennett and Gilles Prasad in 1984, and hence the name BB84. It is also called as the prepare and send model because like here we prepare the photons and then send from the receiver to the no, from the sender to the receiver. So it is called as the prepare and send model. And the main motive here is to encrypt and share a key only securely. Like it is not like the whole data is encoded in the photon states and it is shared. It is like only a key. We encrypt only a key and then we share it. So here we use mainly two channels. One is the quantum channel, which is to transmit the photons and the particles, and the second one is the public channel, which is used to share the basis information. I'll explain what the basis mean in the next slide. Yeah, so let's see first what happens in the sender's side. The sender's side is called as the Alice, as I already told. Alice has two RNGs. RNGs in the sense random number generators. So one of the RNG will first create a bit string of zeros and ones, like zeros and ones in the sense it will be like a string. And then the second RNG will choose one of the bases for that. Like there are two bases. Here you can see, like there are two bases, a rectilinear basis and a horizontal, like diagonal basis. A rectilinear basis in the sense one can be 0 degrees and the other one is 90 degree. And diagonal basis in the sense it will be 45 degree and 135 degree. So the second RNG, what it will do is it will choose one of these bases, either rectilinear or diagonal, and then it will encode the bit accordingly. So if it is 0, yeah, you can see here. So if the bit is 0, then in the rectilinear basis, it states that it is 0 degrees. And if it is 1, it is 90 degrees. And in the diagonal basis, if the bit is 0, it is 45 degrees. And if it is 1, it is 135 degrees. This is just an example. Like it can be ulta also, like the alternate method can also be used. This is just an example. Yeah, so now let's get back to what Alice did. And after encoding these, like the zeros and ones will be transformed into the states of photons, like photon states, and then it will be sent through the quantum channel, which I told before. The quantum channel can be either of two types. It will be like a fiber optics cable, or we can use free space communication also. And then, like after it has been sent, the Bob will receive these. Like the Bob is the receiver. So now let's see what happens in the Bob side. So Bob, after receiving these photons, it doesn't know which basis to use to measure them, right? So this will again use another RNG. Bob will again use another random number generator to decide which basis to use. So it will again choose one of the rectilinear and diagonal bases, and then it will measure the received photons. But now, like if you uh, here you can see the bit string, like the 01001011. And now, if the Bob uses the same basis as used by the Alice, then it will interpret the data the correct way. Like whatever has been sent will be interpreted. But if it uses a different basis, like if suppose Alice has sent in a horizontal basis, like I mean the rectilinear basis, and the Bob had used a diagonal basis, then the interpretation will be wrong, right? Like it won't be correct. It will be entirely random. It can be like 0 or 1. It is not correct. It won't be correct. So this is why, like after measuring all the photons, what Bob will do is it will now like as I already told, the basis used by Alice will be shared to the Bob through the public channel, like separately. So now Bob will get this information and it will compare the bases, like whichever are same and whichever are not same. So accordingly, what it will do is it will drop the zeros and ones which are interpreted wrongly. Like if the bases have not been same, those zeros and ones will be dropped and the key will be shortened, right? So this shortened key is called as the shifted key. So now again, like after getting the shifted key, we should know if it is like secure, right? We should check if it is secure or if there is some eavesdropper present in between. For this sake, Bob, what it will do is it will again compare the shifted key also simultaneously with the bases used. Like as all the bases used are same, like if the if the bases used are same, then of course the zeros and ones should be similar, right? If it is not same, then there is some eavesdropper present. And to calculate this, this is what is called as the quantum bit error rate, QBER, as I told you before. So if this is like for BB84 model, it is 11%. Like the maximum tolerable error rate is 11% because these errors are not only caused by the eavesdropper, it can be due to some atmospheric noise as well as the loss of signals, etc. So the maximum tolerable error rate is 11% for BB84. So now after calculating this, if there is more than 11% error, like if the Bob finds more than 11% error, then this shifted key will be dropped as well. So it won't be used. So and if the other case, like if the error rate is less than 11%, then this won't be dropped and the key is secure and it will be used by Bob to securely transmit the original information. Hello. What QKD doesn't do in the sense, like here till here we just saw whatever BB84 model does to ensure secure communication. But now let's look into what QKD doesn't do. There are few drawbacks as well. Like QKD doesn't encrypt the entire data as I told, but only the key. Like as I told, it is only the bit string which is encrypted and shared to Bob, not the entire data, because if we try to do so, then a large amount of data will be lost in the process of communication, like through the channels and through the noise, etc. So this is not possible. So again, we should go for the classical encryption algorithms to encrypt the normal data anyways. So now QKD, and the second point is QKD is very effective only till the distances of less, like 100 to 200 kilometers, like fiber optics QKD. It will be efficient only till 100 to 200 kilometers. If we go more than that, then there will be significant amount of loss of signals. So it won't be secure again. Like not secure, the data will not be entirely transmitted. So that is why the fiber optics QKD is a very bad choice, and that is why mostly people go for free space QKD, as the error rates and the loss of signals are very less. And the other option is we can use quantum repeaters in the case of fiber optics QKD to reduce this loss of signals. And the third point is that this QKD, quantum key distribution, can be hacked through hardware flaws unless engineered properly. What this means is that if the like for example, one condition is the RNG used here. Like if the RNG of Alice has been hacked, like if we used a classical RNG, like the one which uses the mathematical algorithms, like the one which uses classical algorithms to generate random numbers, these can be hacked and they can be predicted. So if that happens, then this whole QKD will also fail. So that is why we go for, not us, like the Japan has already done something. So that is why they go for quantum random number generators, which are like uses. They again use the unpredictable nature of quantum particles to generate random numbers. So they are like more secure than the classical random number generators. Yeah, and the fourth point is that this QKD, it is more like point-to-point communication. Like as I told, it will be from Alice to the Bob. It won't be like a network kind of thing, like a web. So it can't be scaled easily over the entire internet like the public key infrastructure does. So that is why this cannot be used for a large-scale kind of communication as well. So this also acts as a drawback. And here you can see the graph of the loss of signals. Like as you see, The telecommunication fiber, the loss of signal goes on increasing as the distance increases. But in the case of space-based, like free space QKD, it just remains the same, like it is very less. So that is why free space is more efficient than the fiber optics QKD. And now, as I said, the RNGs are QRNGs. So finally, I conclude that QRNGs are better than the RNGs because the RNGs generate random numbers which are not completely random, but they are pseudo random numbers. Whereas QRNGs, whatever they generate, even though they are costly, they are like very random and they are more secure. So now, my friend Balindu will now show you guys a representation with the parts of Alice and Bob, like how they work. So it will be easy for you to understand more than theoretically explaining it.
So hello guys again. We'll go through once the whole protocol so that we can properly understand where the security comes from and how it actually works, right? So now we'll go through it twice. Once where there is no one looking, there's no eavesdropper, right? We're just doing normal communication. And once we'll do it when there's an eavesdropper present, right? So now let's first do it obviously without an eve present, right? So you have a random number generator, a quantum random number generator, as Arudra said, for Alice. You produce two strings of bits, right? One of them being the actual key which has to be sent over to Bob, and the other one to determine the basis, right? The basis being vertical or diagonal, whichever you want to use, right? So now Alice has two bit strings. One is the key, the other one is the basis, right? So now she will start using the source or whatever control electronics she has in order to start sending the signal over to Bob, right? So she will say for one, say one is, say for in the bit string which belongs to what base you want to use, one is vertical, right? So she will encode the information inside the polarization of the photons, right? So the vertical polarization could be 1 and horizontal could be 0, and in the diagonal either one of them could be 1 and the other one 0, right? So now this signal goes to Bob, and Bob has his own string of he has his own quantum random number generator, and he uses this to again put a output a string which he uses as basis, right? Now using this he will randomly select a base, right, on which he wants to measure the incoming photons, right? So this all will be in a timely scale such that Bob knows when Alice is starting to send, and we'll get to know how that is not an issue when we actually have an eve in between, right? So so Bob receives the signals, right? Now there are two cases, right, when Alice and Bob use the same basis to send the information, and when they use different bases, right, with a 50% probability of either. Now when they use the same basis, the photons information will go right through, there will be no issues. Bob will receive it and write it down in his notebook, right, wherever he's storing the signals. And whenever they use different bases, the incoming photon will fall into one of the states, right? It will fall into either 1 or 0 with a 50% probability, right? So it will be random, right? Whatever bit you'll receive will be random, right? So say now this will go on for some 100 500 bits, whatever you want, right? And after that there will be a message from Alice to say the communication has stopped, right? So after that, what they'll do over a public channel, so as to say, right? So public channel is basically what is using it's using RF, right? So it's using normal radio communication to go between Alice and Bob, right? Through that they will share their bases, right? Whatever bases they use. So this is the shifting of key, right? So they will share whatever bases they used, right? So now we already said that there's a 50% probability of them using the same base, right? So half the times they'll use the wrong basis, and now what we'll do is that in the message that Bob has received, he will nullify all of those bits that he has received, which in which they use the non-similar bases, right? Wherever they use the uh, wherever the bases were different, he will remove that from the key. Now that will be the shifted key, right, where they use the same basis. And now here comes the part where which guarantees security, right? So now from the sifted key, they will take some say 50 or 60 bits and compare over again over the public channel whether what Alice sent was received by Bob, right? And whenever it's not, they will note it down. And in the end, they will calculate something called the QBER, right? Which Arudra talked about, the error rate. Now, since there was no eve in between, it is guaranteed that the error rate, the QBER, will be less than 11% in this communication setup. And we will say that there was no eavesdropper in between looking at the communication, right? And hence the communication is secure. And whatever key you have left, right, the key that you didn't use for safety, for calculating QBER, that will be a key that is only with Alice and Bob, and no one else has that key, right? Now, what gives security is the fact that if Eve tries to look at these signals, right, what they will have to do is that they will also have to prepare a base, right? They will have to have a base in which he's measuring the polarization of these photons, like Alice and Bob, right? But the thing again is, Alice and Eve can have different bases, right? They can choose different bases with a 50% probability, even if Eve knows what bases Alice is using, which is already something hard to do, right? You have to know what exactly is the polarization of what Alice is sending. Eve has to know that, right? So say Eve knows that by any means, right? Still, half of the bits that Eve will read will be wrong, right? Now, for someone to say that you're acting as Eve, what you'll try to do is you'll read the information and then you'll try to send it to Bob, right? The similar state you'll try to send to Bob. Now, the thing being, according to the lone cloning theorem that Arudra told, you can't exactly clone a state, right? So, Eve, in theory, right? So, in theory and also all terms of practicality, can't act as Alice. So, Eve can't physically go and read the message and then send it to Bob, right? So now if Eve will just read the information, then Eve will destroy the communication, and then Bob will know that there is something happening, and you'll say that the communication has been compromised, right? Then you'll know that someone has looked at your message, right? So basically what quantum communication allows you to do is that when you send information from one place to another, you know it's safe, right? You know that no one else has looked at this information, and you can use it as your key to further, so you wouldn't actually share messages across this network. You will actually share keys, and then you'll use those keys to encrypt your messages, right? So you'll use the key to encrypt your message, and since no one else in the world knows the key, then you basically, the communication is secure, right? So you have no issues whatsoever in saying that the communication is secure, and this is what QKD enables. So one of the ways to do this was BB84, what we have told just now. There are many other protocols that have been theorized, right, and also been implemented on a small scale, which Nikshep will talk about, right? So Nikshep can talk now.
Good evening, everyone. So my name is Nikshay. In the next 20 minutes, I'll be explaining about two protocols which are based on quantum theories. So uh, before that, let us very quickly again go through some of the basics of quantum mechanics. You have seen this already explained by my friends, but we will just revise this very quickly again. So the first one is superposition. So what happens in, as you can see in the pic, what happens in classical communication is a bit is either 0 or 1. But in quantum communication, a qubit can be both. Like it's a superposition of both 0 and 1. So what happens in classical communication is that any hacker may hack and read the inscriptions, but in quantum communication, it would be not possible to do so. The second is the quantum entanglement. So quantum entanglement in simple words is that if two particles are in quantum entanglement, irrespective of the distance, so if two particles are in quantum entanglement, so irrespective of the distance, if the state of one particle is measured, then the state of another particle would be automatically known. So this was quantum entanglement in simple words. So the next is the no cloning theorem. So the no cloning theorem just says that any quantum state cannot be copied exactly as it is. So this was no cloning theorem. So and then is the measurement basis. A measurement basis is a set of reference states or orthonormal vectors used to define the possible outcomes when measuring a quantum state. So in short, it's just a basis. So in short, measurement basis is just a basis used to measure the quantum state. So these were the four important basic principles of quantum communications. Because in classical protocols, so like any hacker may read the inscription, but in quantum communication, the keys would be in superposition. And if anyone tries to measure it, the quantum state would just collapse into 0 or 1, making it clear that there was an attempt to tamper the data. So so yeah, now let's look into another important concept in quantum communication. That's the Bell's theorem. So Bell's theorem states that if the world were governed by the local realism, then the outcomes of certain quantum experiments would obey certain mathematical inequalities. But in the real world, quantum experiments violate those inequalities. So in simple words, it just means that see there are some mathematical inequalities. They are called Bell's inequalities. So if local variables of the system does follow the Bell's mathematical inequalities, the system is in it just means that the system is in quantum entanglement. And if it violates the Bell's inequality, the it just means that the system is not in quantum entanglement. So this was Bell's inequality. So now let's look into the CHSH inequality. So this equality is just a special case of the Bell's inequality. So when there are two pairs of measurement bases, so CHSH inequality is just a special case of Bell's inequality where there are just two pairs of measurement bases. So consider two pairs of measurement bases A, B, and A dash B dash. So yeah, as you can see the equation in the slide. So so E here is just a correlation function. It's the expected value. So we will not jump into the mathematical detail here in this part. Just understand that E is a correlation function calculated mathematically. So using this equation, the S is calculated. So S here is the CHSH factor. So the CHSH inequality states that if S, which is the CHSH factor, is greater than 2, it just means that the system is in quantum entanglement. And if S is lesser than equal to 2, it violates the inequality and it just means that the system is not in quantum entanglement. So this was CHSH inequality. So we would be using this inequality to understand these two protocols. So yeah. So as the things are clear about the basics of quantum mechanics and the Bell's inequalities, so let's look into the protocol. So the first is the E91 protocol. So this protocol was proposed by Arthur Eckert in 1991. So this protocol uses the concepts of quantum entanglement, Bell's inequality, all the things we just saw now. So and then so the security of this protocol is based on the Bell's theorem. Note that the security of the protocol of this protocol is based on the Bell's theorem. So this E91 protocol allows two distance parties. So let's say by convention, Alice and Bob, to generate a shared secret key using entangled particles. So yeah. So now we'll just see the overview of this protocol. So consider a source. So the source can be trustable or non-trustable. So consider a source that generates many pairs of entangled photons in Bell state. And now what's Bell state? What is Bell state? So Bell state is nothing but a state of quantum entanglement. So there are four Bell states, as you can see in the pic in the slide. So these are the four Bell states. So a photon in the Bell state just means that the photons are in quantum entanglement, and measuring one photon would just determine the state of another photon also. So consider a source which can be both trustable or non-trustable. So that generates many pairs of entangled photons, right? So each photon in the entangled pair is shared between Alice and Bob. Say like there's a pair. So in that pair, one photon is given to Alice, another is sent to Bob. So now what happens is that Alice and Bob now randomly choose a set of measurement bases each. So yeah, let's understand this by seeing this pic in the slide. So as you can see there, so there's a source which produces entangled photon pairs. So one photon is sent to Alice and another is sent to Bob, as you can see in the pic. So so Alice has this measurement basis A1, B1, and C1. So and Bob has this measurement basis A2, B2, and C2. So now what happens is that Alice and Bob each receive a photon. Say they receive many photons, like the source produces many entangled photon pairs, and they both receive many photons. So while they receive a photon, they just choose a random measurement basis from their respective base. So they just choose a random measurement basis from their respective base, and they measure their each photon. So in each of their measurement, so they receive a photon, they just pick a random basis and they measure. So in each measurement they record two things. The first is the measurement basis they're using to measure that photon, and the second is that the outcome of the measurement, that is the result of the measurement. So after many rounds, Alice and Bob publicly share their measurement basis they used for each round. See, note here that they are not sharing the outcomes of their measurements. So after many rounds, Alice and Bob publicly they share their measurement basis they used for each round. So they using this recorded data, they perform two important tasks. So the first is the Bell's test, the other is key generation. So one set of the bases which is compatible is used for key generation and remaining for the base test. Say the measurements done in C and C1 basis is used for key generation, while the basis A measurements done in the basis A1, B, B1 are used for Bell states. Like consider. So using that, so as we saw the CHSH inequality, so using that equation, they just calculate the S, which is the CHSH factor, using the A1, B, B1 basis. So yeah, now if yes, which they calculate turns out greater than 2, it means that the system is in quantum entanglement, as we saw in the CHSH inequality. Because see, if there was an attempt to hack the data or tamper the data, so the quantum state would have collapsed into 0 or 1, right? So and then the quantum entangle would not have been confirmed. Like yeah. So but when S is greater than 2, it means that the system is in quantum entanglement, which means that the communication is secure and there was no attempt to read the data. And now, when the communication is proved to be secure, now Alice and Bob use the measurements done in C and C1 basis to generate a key. Yeah, this was E91 protocol. So yeah, now why E91 protocol? See, the first thing is that E91 protocol is more secure than BB84 protocol because it uses Bell's inequality for security test, and then this protocol is based on quantum theories. See, and this protocol is independent of the nature of the source. Because see, see, the source can be either trustable or not trustable. Because there's a security test, and we are confirming that the communication is secure is using the Bell's inequality. So this protocol is independent of the nature of the source. Hence, the E91 protocol becomes the foundation for device independent QKD. Yeah, this was E91 protocol. Now, yeah, I hope it's clear. Now we'll see the second protocol, which is the BBM92 protocol. So this is also entanglement based key quantum key distribution protocol. So it's the same. It's see basically E91 and BBM92 are almost same. Let's see the overview of this protocol again. See in the pic in the slide, consider a source which produces entangled photon source. So this source can this source also can be testable or non testable. So source consider source which produces entangled photon source. So one in among the pair, one is sent to Alice and another is sent to Bob. So now, see now, Alice now the see now Alice and Bob would now randomly choose among two fixed bases. As you can see in the pic, Alice has measurement bases A1 and B1. Even Bob has the measurement bases A1 and B1. So Alice and Bob would now randomly choose among two bases. So as they receive their photons, they just randomly choose among that two fixed bases, and then they measure their respective photons. So in each measurement, they record two things. Again, they record first is the chosen basis in which they are measuring the photon, and another is the result of the measurement. So yeah, and after many rounds, again Alice and Bob publicly announce which bases they used for each round. So yeah, so now here also they're just announcing the basis they used for a measurement, not the outcome. So they announce the basis which they used for each round. So now they discard rounds where the bases don't match. So they just discard all the rounds where their bases don't match. And in the rounds where they choose the same basis for measurement, they use it for extract. They use it to extract key bits. So this was BBM92 protocol. So so now let's see how is the eavesdropping check done here. So so in this protocol, they just compare a small sample of key bits publicly to compute the error rate. So now let's so they just compare a small sample of key bits publicly to compute the error rate. So now what is error rate? So the error rate tells how often Alice and Bob's measurement results don't match the expected quantum correlations. Like, see, as they assume that the source is producing photon pairs in phi minus state. So the phi minus state is also known as the singlet state. So you see, this is one of the states of the four Bell states, as we saw before. So phi minus state is one of the state of the four Bell states. So they just assume that the source is producing photon pairs in phi minus state. So what happens here is that when they're using same basis, so if Alice measures his photon to be 1, then the Bob must measure his photon to be 0. So if not, it's just called a mistaken mismatched reading. So using that, the error rate is computed. Like the error rate is computed using the formula number of mismatched readings divided by number of total readings. So yeah, so the thing is, this error rate may be due to noise also. Like if there is noise between Alice and Bob and there is some disturbance in the signal, so this error rate or mismatch readings may be due to noise and disturbance in signals also. But if the error rate is greater than the threshold, some point, so there can be a suspicion that there was a eavesdropping. But it can also be due to, see, note that it may be also due to a more noise or more disturbance in the signals. Like, yeah, but see the but as a security measure, if the error rate exceeds some threshold, so it just consider that the communication is not secure and the communication is stopped. So yeah. So now you can ask, how is it secure? So the first thing is this protocol security is based on this fact. As we saw that they assume that the source is producing photon pairs in phi minus state, which is a singlet state. So when Alice measures 1, then Bob would have to measure 0 in that state. So this is the concept they used they use it for this protocol security. So and then unlike E91 protocol, this protocol does not use Bell's inequality test as a security test. Yeah, and this is also a source independent protocol. So now let's see some of the differences between E91 and BBM92 protocol. The first thing is that in E91 protocol, Alice and Bob would respectively choose a random set of bases for themselves. As we saw in E91 protocol, Ali said A1, B1, C1, and Bob had A2, B2, C2. But here in E91 protocol, the thing is that there are two fixed bases, A1 and B1. So when, like, while measuring their photons, Alice and Bob just choose randomly among these two bases only. So another difference is that E91 protocol uses Bell's security test, Bell's inequality as a security test, but a BBM92 protocol just compute the error rate. So, so the drawback of BBM92 protocol is that, see, they are ideally assuming that the source produces photon pair in singlet state only. See, the main drawback is that they are ideally assuming that the source produces photon pair in singlet state only. So I told you what is singlet state is. Singlet state is one of the four Bell state we saw that. So yeah, so as we said, if the photon pairs are in that state, if Alice measures one, then Bob would have to measure zero. So they're ideally assuming that the source produces photons in singlet state only. And so if the source produces photon pairs in all the four Bell's tests, then the BBM92 protocol would fail to do the security test. But E91 protocol would be efficient in that case. So this was the drawback of BBM92 protocol, and I hope these two protocols are clear. So we'll just now look into some of the present day developments in quantum communication. So yeah, the first is the Misha satellite. See, this satellite was launched in 2016 into the orbit of at an altitude 500 kilometer. So it was a quantum experiment science satellite. So it demonstrated entanglement distribution from a satellite to two ground station on Earth, like two ground stations on Earth, which are approximately 1,200 kilometer apart. So with a violation of CHSH inequality. So as we saw in the CHSH inequality, so if S is greater than 2, it means that the system is in quantum entanglement. And then in this experiment conducted by the Messier satellite, so the S, which is the CHSH factor, turned out to be 2.37 plus or minus 0.09. So 2.37, which is greater than 2, which means that it successfully demonstrated quantum entanglement. Yeah, and the next is the Quantum Encryption and Science Satellite, QEYSSAT. So, this is a Canadian space agency. Its primary mission is the demonstration of distributing secure keys between ground station at least 400 kilometer apart. So, so yeah, this was QEYSSAT satellite. So the next, so yeah, so next is the Cube satellite. So this is also a spacecraft. It is yet to be launched. So the main purpose of this satellite is to investigate possible QKD applications and also for testing of BB84 protocol. So yeah, and then recently the combined research done by DRDO and IIT Delhi also have demonstrated free space quantum secure communication over 1 kilometer range. So yeah, this is also being seen as a very big leap in quantum research of India. So yeah, uh, these were the present day development modules. So yeah, the present day developments. So the next part will be taken by my friend Tanuf. So yeah, Tanuf can take over. Thank you so much.
Hi. I'm going to talk to you about how to come to this field. So, like, how you can come and work on a communication and stuff. So I'll be mainly talking about two things. One will be how to come to this aspect, and the future aspect of quantum communication. Mm, so, give me a sec. Yeah. So the future pathways. To reach quantum communication, you need to basically know three topics. One is quantum mechanics, Second one is signal processing and photonics and optics. Apart from this, a bit of lab work would also help in quantum communication. So, in quantum mechanics, the courses that usually are required are quantum mechanics 1 and 2. This will teach you the basic level of quantum mechanics, and 2 will do the system level of quantum mechanics. Then, quantum computing and information. This will basically contain most of the stuff which was taken today in depth, like what are qubits, what are the different protocols used, and stuff. Then you need quantum optics, which will talk about how optics works in the quantum mechanics region, and then open quantum systems, which integrates all the three courses to build quantum systems. Then you have signal processing. So signal processing is is required in quantum communication because you are basically sending information through signals. So some courses that would help are digital signal processing. So this would include like sampling, then digital Fourier transform and stuff. Then random signals and random noises actually. This is for understanding how noises are produced in any system. Then information theory and programming and modulation. These are required for your understanding of how signals and how communication in general works. Then about photonics and optics, you need to understand the fundamentals of photonics, such as like this will introduce you to like equipments that are used for this, such as lasers, half wave plates and stuff. Then nonlinear optics. See, nonlinear optics is required because half of the processes explained in this were nonlinear in nature. And finally, integrated photonics. That is the chip level integration of photonics. And coming to the future of what quantum communication holds is this can lead us to send more information across our space. So like it can help us in future missions to Mars, or even future establishing an intergalactic internet, or so, some sort of that. So that's all. So thank you for attending the sessions. Now we are open for any questions. Any questions, anyone? Please unmute and
Hi Dhanuv, I'm Aryan. So I had a question.
yeah.
Yeah. So it pertains to like what are the applications of specifically quantum computing and communications towards the like does it involve defense? Does it involve finance? I just wanted to understand that.
Okay, so like I told you about applications. So applications can be our main, like the main advantage of quantum communication is the security it offers in the current situation. So it would be much more useful in defense if we are able to communicate like coordinates and stuff through these channels, allowing for more secure transmission of data. Then banking or finance, like the data is considered to be the new money in the current situation. So finance, obviously it would be helpful if like I am using a quantum channel to transmit my financial records or perhaps money and stuff.
Okay, got it. Thank you.
Anyone else have any questions? Not just directed towards me or towards all of us, any part, any topic. So you will be able to access this YouTube live stream in the future. So you can go through the slides through that.
Yeah, so we have come to the end of the session. We'll be attaching a Google Form link in the description of the YouTube channel, YouTube video. So please try answering those questions and do submit the form so you can assess yourself like how much you've learned through the session or something like that. So yeah, the session is officially over. We can end.